Hey there, everybody. This is Jacob Reka. Maybe you guys have seen my previous videos. I usually post them to LinkedIn and YouTube. This is probably my third or fourth video that I've posted. Most of the stuff that I write about on LinkedIn is environmentally related, and then also recently a little bit of intellectual property uh, content, I guess you could say. Because I've been working with the Purdue Research Foundation for the past year, and I'm interested in that area. One area I'm also interested in, I've been interested in for a long time, is baseball. Baseball statistics, watching baseball. I really do like watching baseball. So I think it was last week I was watching the Cleveland Guardians, my favorite team. They were, I don't know who they were playing, but Cal Quantrill, a starting pitcher, was pitching that day, and one of the announcers for the Guardians, he said that Cal Quantrill gets a lot of run support, um, and to me, I kind of wanted to, I was thinking about it, like I wonder if there's something to that. Like, is there like a reason for that? His ERA on the year is like it's kind of high. It's like 5 point something. Actually, I can basically this is going to be me talking about some data analysis and code um, that I created. So I guess I can go to the code now, but I'm kind of jumping the gun, so to speak. But anyway, I'll go to this code to talk a little bit about Cal Quantrill. So this is a pandas data frame in Python. Let's sort by the picture here for first name. Cal Quantrill. So yeah. Oh no. Okay, no. Run support was 5.2. And ERA is 3.56, which is pretty good. But still, the run support is like quite good. 5.72. It's definitely above league average, I would say. I don't think I'm wrong on that again. Yeah, that's definitely above. I'll talk about this graph that I made, but 5.72 is definitely above it somewhere up in here. So yeah, I don't want to jump the gun. So kind of going back to my little monologue. So I was initially I was thinking about different sort of. I kind of like to do small little studies that only take a few hours to do. So I was thinking, what are some areas of this sort of causality of run support, different causality of run support differences that I could look into. So basically, the most important part of this analysis, in my estimation, I mean, I don't really know that much about baseball statistics, but I wanted to see if there's a correlation between ERA, earned run average. It's a metric used to, it's basically a calculation of the number of runs that can be assigned to a pitcher on average over the course of a 9 inning game. I wanted to see if there was a relationship between ERA and run support. And I was thinking I wanted to look league wide. Part of sort of if there was actually what I was initially expecting possibly was that for pitchers with a higher ERA, their run support would maybe be higher. I was thinking because maybe the players know when a certain pitcher who is going to give up some runs probably is out there. Maybe they need to step up their game a little bit. I don't know. Yeah, that turns out to definitely not be true. But I was thinking that might be it. I couldn't really figure out any other reasons. So, part of the reason why I did the analysis was to figure out if there actually is a relationship between run support and ERA, which I figured out that there might be one, but it's a minimal relationship. The correlation is very weak between the two parameters, at least for the 2022 season data, and that's so many data points. I mean, that's thousands of games right now. So 162 games in a year. You have 30 teams, so 30 pitchers starting those games, and in each of those outings, you have a run support calculation associated with that, an ERA calculation that goes into that. So yeah, I mean, there's been would that be like at least probably 30 times 150. So like, yeah, 4,500 at least data points. So that's probably a lot. And these data points and this relationship, or lack thereof, is probably, it probably holds over a multi-year period. So um, initially I was thinking that, if there was a relationship in 2022, we could kind of look back at 2021 and 2020 and see if, kind of longitudinally, if there was anything, if, the behavior was similar. But since the relationship is pretty weak between run support and ERA, I decided to just kind of stop at 2022 data. So yeah, so without further ado, I'll kind of go into the data analysis. I'll try to keep this somewhat short. So I kind of got interested in data analysis when I was actually earlier this year, this past summer. I was working on a data analysis project for my capstone project for my master's program. So I got a little bit of exposure to Python, and this terminal here, it's called Spider. I like it. It's a lot better than when I initially learned Python. I was just doing it in like the idle window, and this blows that out of the water, to be honest. Especially like the variable explorer is really nice. I mean, I was able to find CalQuantRel really easily with the data frame exploration, and then the plots are yeah, it's easy to toggle between the plots. So yeah, so let's kind of talk about how I got the data. So I searched on the internet for maybe half an hour trying to find data. Ended up finding it at a sports betting website, Odds Shark. I'll put this URL here. This is the 2022 all MLB pitchers ERA, so their ERA across all their starts, and their average run support per 9 innings. So extrapolated out to 9 innings, similar to ERA, extrapolated out to 9 innings. That's an average over all of their starts. The runs that are there to support them for each of their outings on average. So I've never imported data directly from the internet, but I mean it's pretty easy. You can do it actually with the pandas library. You can use this pd.read HTML. So if the pandas module realizes that recognizes that the data is in like a table format, it can actually just directly read that into Python as a data frame, which is like the most common data structure in pandas, which is really nice. And actually, I don't have the initial one that it pulled in, but it's pretty similar to the one I was just showing. It was bigger than this. There were probably maybe like 125 more entries in it, but I ended up taking some of them out, and I'll talk about that later. But yeah, it has all the pitchers. Initially, I had all the pitchers that have made starts in Major League Baseball this whole year. So it was like over 300, which is quite remarkable because that's over 10 per team on average. And teams generally have 5 starters. So I guess some teams are doing that differently now. Tampa Bay among them. That's a tangent. Anyway, you have so it was over 300 pitchers. Number of games they pitched, starting pitched, listed, average run support for each of those games, wins, losses. I didn't use that data, and then ERA. So yeah, that was pulled in directly from the internet, from oddshark.com, and I put that into I used pandas to put that into a data frame format, and then I just made a plot. I just wanted to see what the data looked like. So I did a scatter plot, and that's what this plot has more data. I'll go back to the initial plot. This is the initial plot. I had one of these labeled. Yeah, this is the initial plot. So I looked at this and I said, okay, I think the first thing I need to do is get rid of some of these outliers, like an ERA of 20. Like that's just not, like if a player has an ERA of 20, like for multiple starts, then they're not going to stay in Major League Baseball. So yeah, these are like players that made like 1-2 starts probably, and also like a run support of like 17, 18, 19. Like that's super high. Like also probably a player that made like one start in the team. He pitched 5 innings and he scored 10 runs and over those 5 innings. So yeah, I was the next step was eliminating those data points because those are outliers. So part of that process was eliminating pitchers who had made less than 5 starts. I guess that was pretty arbitrary, but that was this took me a little while to figure out how to get the code to work to be able to do this. So what I ended up doing was I cycled through the whole data frame, which has, I think it originally had like six columns. I actually ended up adding one because I had to re-index the list after I deleted some values. So yeah, if so basically this function, it's cycling through all of the whole length of the data frame. So it was over 300 entries originally. And then, so games was one of those column names. So if that column, data frames, that DF, that's the name of the data frame, if data frame games so if each row entry of the games column, if that entry is less than 5, then I appended all those index values to this players to delete 1 function. And it was over 100 deletions with the less than 5 limit. So, and then I used this fancy function that Pandas has, df. Well, df was the name of the data frame, but dot drop. And the labels that I was dropping, the indices, was players to delete 1. So that whole list. So yeah, that eliminated like 100 players. And then the reset indexes, there was a problem when I was doing this sort of thing again. There was a problem I realized when, so Pandas, actually when you delete values, it doesn't, it'll actually like leave the original indices. So like, you'll see like at the end of this, like you end up with like 346 for Javier Assad as that index. But that's like the original index. Really, there's only 231 entries, 231 row entries. But the original index for Javier Assad was 346. So over 100 were deleted initially, and then like 15 were deleted with the outliers stuff I'll talk about in a minute. But yeah, I had to, that's what the resetting of the index, that's what these first values here index, these like all increment by 1. So that's what resetting the index was for. It added a column, but it allowed me to do the incrementing again, which I used down here. So yeah, I found this, somebody was careerfoundry.com. Somebody was, I was trying to, see if anybody else, and I was sure somebody had done work on how to determine the outliers in the data set. So I learned about this back in stats class. This seemed like a reasonable approach. So, this is your first quartile, your third quartile. So, so I defined using the person from careerfoundry.com. I basically just copied and pasted what they did and applied that for this data. So I got quantiles for each of the columns in the data frame, quantiles at the 25th and 75th percentile, so the first and third quartiles. And then I got the IQR by subtracting those. And then lower bounds and upper bounds for each of the games, which I didn't need, wins, losses, ERA, run support. I was only really concerned about outliers for run support and ERA because those are the 2 variables I was analyzing. And then, so yeah, setting lower and upper bounds based off of 1.5 IQR below the first quartile as the lower bound, and then 1.5 IQR above the third quartile as being the upper bound. And then this is for sort of creating lists to, actually I only end up using this one, lists to identify the outlier players based off the ERA and run support stats. So that's what this is here. And this is a problem I was having with once I eliminated those 100 values of players that had less than 5 games. And it pandas, the data frame, it didn't change the indices back to just incrementing by one. There was a problem here because when I was cycling through this range, these are all if statements. So I didn't do any else if like there were certain values of data frame era. So that's ERA. This column. So looking at just the ERA column and then the J being incrementing the rows. So like row 0, row 1, row 2. But like, for example, like row 2 was gone because that player was deleted because they pitched less than 5 games. So then, DF era 2 didn't exist. So I was getting errors. So I had to figure out what was going on there. But yeah, I eventually figured it out. And this is what the reindex value is. So if DF era J, so if that row entry, this is for the whole length of the data frame. If the row entry of ERA is greater than the upper bound at 1.5 IQR above the 75th percentile, then I appended that value to a list. And then the same thing if the ERA was below the lower bound, and then the same thing if the run support was above the upper bound, and the same thing if run support was below the lower bound. So basically identifying those outliers. There weren't that many. There were maybe like 10 or 15 outliers. I can actually find that. Let's see how big this list was. Oh, actually just 9. Yeah, there were only 9. That's players to delete too. There were 124 in that first list. So yeah, a lot of like the paring down of that list happened with eliminating players that pitched less than 5 games. So yeah, so that kind of gave me a more concise data set to plot, which is what this one is. So these blue dots are the original data points, outliers, and less than 5 game pitchers included. And then these, I think it was it orange, green, I don't know, dots, that's the sort of like the cleaned data. So yeah, so this is just plotting. And then I plotted I plot just with like that cleaned data, so to speak. So that's what this is. So I looked at this and I realized that my initial prediction was definitely not true. Any of sort of like that longitudinal stuff I was going to maybe do later, or I was also thinking about doing some stats on like comparing run support for the highest ERA and lowest ERA pitchers and seeing if there was like a material difference, a statistically significant difference between those two groups. But that doesn't really seem that useful after looking at this data. And I saw and I was like, okay, really, there's no correlation here, but let's maybe just let's get a least squares regression line on there, and maybe calculate a correlation coefficient and see if just kind of just confirm. So that's what this is all about. This is kind of some gymnastics. I ended up finding on the NumPy documentation about how to do their form of the least squares. I could have swore I'd done this before, but I didn't do it this way. Yeah, so there was just some, I guess it's not that complicated. These are like arrays. This is a vertically stacked NumPy array. So the DF era is the ERA. DF ERA is that's the entire, all the values, all the ERA values, and then MP.1 is just a ones matrix of the ones, and that's transposed. I'm not sure exactly what the meaning behind that is. This is what they said to do on the NumPy documentation, and then that's what this function is. This function is least squares regression. So A is this, and then this is like the Y values. So yeah, that gave this line here, and all this is about plotting this. So because I knew it was a line, I just chose 2 points. I went here and found the 2 points that were at the ends of the ERA sort of spectrum. So yeah, I looked here and I was like, okay, which 2 points can I use? So one of them is Justin Verlander, who's having an awesome year, 1.78 ERA. So he used that sort of initial point, and then Spencer Howard, I don't know who that is. 7.41 ERA. So those were the two that I ended up using, those two data points to create the bounds of the lines. That I created a line that fully spans the graph. So those ended up being index positions 2 and 161. Yeah, so I appended those to a list and then calculated what the Y values are predicted for those two. The Y values being, I guess I could have called those predicted run support values with that least squares regression line are. That's what the Y1 and Y2 are. So the first one's for Verlander and the second one's for that other guy. If he ever ended up watching this, I'm sorry. I don't know who he is. Hopefully he has a good career. And then I appended those Y1 and Y2 values to a list, just like I appended these ones to a list, and then did a plot of this, and I made the line green so we could see it. Yeah, so this is showing there's some negative correlation actually. So when I was expecting a strong, well, I guess strong positive was probably a little bit too ambitious, but I was expecting some positive correlation, and this is pretty clearly negative. I mean, the correlation is not strong. That's part of what I did next. This is really nice. I found this on machinelearningmastery.com. Gave some information on how to just calculate a Pearson correlation coefficient. And I also was on the SciPy. That's a SciPy function. It's really easy to do that. And when I did that, Pearson's correlation is negative 0.192. So it's negative because it's a negative correlation. 0.192 is pretty weak. So yeah, I mean, there's really not a relationship between run support and ERA. So yeah, that's what I found with this. A little bit disappointing that I don't have some awesome result, some sabermetrically changing baseball statistic on my hands. But yeah, I guess I know now, and maybe if you're interested, maybe now that when an announcer on the TV screen says that a pitcher has a lot of run support, it's just kind of an anecdote. Like there's really nothing to that. Like there's nothing to like maybe the players play really well for that guy and really they know they need to hit for the guy. Maybe that is true for some cases, but that's not true league wide. Certainly, if anything, it appears that if the pitchers that have higher ERA are on the mound that day, there's actually a little bit less offense from their team. So yeah, that's it. Hope you found this interesting.